The advent of the 3D printed minimalist lightweight micro turbojet engine. The advent of additive manufacturing has reshaped aerospace propulsion by enabling complex, integrated designs that radically reduce weight. China's Aerospace Propulsion Institute successfully leveraged these advances to independently develop the minimalist lightweight micro turbojet engine, marking the country's first fully 3D printed turbojet in the 160 kg thrust class to complete a flight test. China's new micro turbojet marries multidisciplinary topology optimization with laser powder bed fusion 3D printing. Computational models identified where material could be removed without compromising strength, then the engine's components were printed as single, highly integrated structures. This approach bypasses traditional casting and forging, simplifies assembly, and realizes internal geometries once deemed impossible. Multidisciplinary topology optimization tailored for additive processes. Laser powder bed fusion enabling fine, high-temperature metal parts. Integrated component design to minimize part count and assembly steps. In the Inner Mongolia Autonomous Region, the engine soared to 4,000 m altitude under real flight conditions, delivering a peak thrust of 160 kg. Preceded by rigorous ground trials, covering thermal stability, thrust curves, and life cycle loading, the maiden flight fully validated the engine's reliability and stability. Traditional turbojet engines consist of over 2,000 parts and require years of meticulous craftsmanship. The manufacturing tolerance of turbine blades must be controlled within 1/10 the diameter of a human hair, and the cost of a single blade is comparable to that of an equal weight in gold. To reduce engine weight, research teams often need to redesign the engine from the ground up. Multidisciplinary topology optimization algorithms, known as intelligent carving knives, can rapidly remove redundant material in virtual space, cutting the number of parts by 70% and reducing structural weight by 40%. Core components such as compressors and combustion chambers, which traditionally require assembly, can now be 3D printed as single metal pieces. This eliminates gaps, increases strength, and triples service life. Using 3D printing technology, a 100 kg turbojet engine can be designed and test-fired within just 6 months. Printed components account for over 70% of the engine, and costs drop to 1/5 of those for traditional manufacturing methods. For the 160 kg thrust class engine, compared with the expensive Canadian PT6 engine, priced at $2 million per unit, used in the US Reaper drone, the cost of a 3D printed turbojet in China is expected to fall to 200,000 renminbi. Testing by a logistics company in Shenzhen shows that cargo drones equipped with 3D printed engines can achieve a range of up to 800 kilometers while carrying 60% more payload. SF Express and JD.com have urgently adjusted their strategies. Low-altitude logistics costs may be halved. This breakthrough closes a critical gap in China's domestically produced propulsion systems, reducing reliance on foreign sources for small turbojets. The lightweight 160 kg thrust class engine is primed for high-speed unmanned aerial vehicles, extending range and payload capabilities for surveillance and reconnaissance missions.